The topics of redox and electrode potentials and the transition elements are very closely linked on the OCR specification in A-level chemistry in Module 5. In this tutorial, I'm going to be taking you through selected exam questions from the 2017, 18 and 19 series of Paper 1 exam papers. Please check the video description for information and links to these papers and also the timestamps so you can go straight to the paper that you're interested in. Starting off here with question 22 from Paper 1 2017 on the OCR specification. The question is all about redox, electrode potentials and feasibility, and you can see we've been given a little snippet of the electrochemical series here, and we've got 4 redox systems in a table, all with their standard electrode potentials, and notice how they're all written in the reduction direction, which is what we would expect. The highlighted purple sections here indicate that we are drawing the apparatus for a cell that is based on redox systems 1 and 3. So if you have a look at the apparatus that I've got just down here, I always show the oxidation half cell, so that would be the anode or the negative one, I can describe it, on the left, but actually OCR in their mark schemes aren't that bothered about this. They will allow you to put it on either side. Obviously read the question if there are any specific instructions in the future, but they're not too fussed about this, it would appear from the marking guidelines. On the left here, because of the components of the half equation in the table, if we have a look just up here, I've got zinc solid metal, and I've got zinc 2+ aqueous on the left. And so my components here are going to be zinc solid metal and 1 mole per decimeter cubed, make sure you've got that label, zinc 2+ for the solution. Notice there are no gaps between the metal electrode, the voltmeter, and the other electrode on the other side, and that the salt bridge and the electrode are both clearly submerged in the solution. On the other side of the cell apparatus, I've got my 2 iron ions, which are from redox system 3, just here. But since I have no solid iron in that redox system, I can't use a piece of iron as the metal electrode, so here I'm having to use platinum. For the standard conditions, you'll notice at the bottom down here, I've listed 1 mole per decimeter cubed solutions, 100 kilopascals of pressure, and a temperature of 298 Kelvin. It's worth noting, although not worth gambling if I'm honest, that in OCR exams, when it comes to the apparatus for an electrochemical cell and then they ask you to state the standard conditions, unless you've got something in the apparatus that's a gas, like if you had the standard hydrogen half cell, for example, they actually tend to have this, the pressure, ignored in mark schemes. Now, for me personally, I'm never going to take the gamble, which is why it's there, but the little red comment here, as you'll see throughout various questions in this, gives you a little bit of extra commentary about what wasn't required, but I would still personally expect to include it. Then for the next part of this, I've got a calculation for my standard cell potential. The way I like to teach this is that the cell potential is equal to reduction minus oxidation. So you've got to allocate which of the 2 redox systems is reduction and which is oxidation. The reduction one is going to be the more positive in terms of electrode potential out of the 2, and the oxidation one is going to be the more negative in terms of electrode potential out of the 2. Here we can see that calculation carefully using brackets should, if I've combined these together in the correct way, always give me a positive answer for a feasible reaction. The sign here is actually ignored, but I have noticed that there are a couple of questions out there for enthalpy and for cell potential where the exam questions now say include a sign on your answer even if the answer is positive. So I've started putting the positive sign on these, even though just in case here with some of these questions, we don't always get that instruction. Moving on with the next part of the question. In table 22.1, what is the strongest reducing agent and the strongest oxidizing agent? Now, all of the redox systems in the electrochemical series, just here, are written in the reduction direction. Now, we can use that to our advantage. Whilst we can't always predict what sequence the electrode potentials are going to be done in, whether they're going to be most positive down to most negative, or jumbled up, or as they are here, most negative at the top and most positive at the bottom, that we can't be certain about. but they should all be written in the reduction direction for an electrochemical series. And if you look through the past papers where a table like this has come up, they have been written in this fashion. Now, as a result of that, we can say that all of these components on the right are potential examples of reducing agents, and all of these components on the left are potential examples of oxidizing agents. Also, we can say that the most negative electrode potential, redox system, is most likely going to be shifting to the left when it's paired up with another redox system. And that's because it's got a greater tendency to release electrons. So I can suggest that this is the most likely one to shift left, meaning that the zinc here is most likely going to be the one that's giving away its electrons. So the zinc is the most powerful reducing agent. In contrast, the manganate down here, so this is the manganate 7 ion just there, MnO4-, is the most powerful oxidizing agent in the table because it's got the greatest tendency out of all these redox systems that we can see due to its very positive electrode potential value here. It has the greatest tendency to accept the electrons. And so when answering the top part of this, my strongest reducing agent is the zinc, and the strongest oxidizing agent is the MnO4-. What you can't do is suggest the entire redox system equation here. You've got to be very specific about which side you select your reagents from. Next one. Electrode potentials can be used to predict the feasibility of reactions. Construct an overall equation for the predicted reaction between the species in redox systems 2 and 4. So I've screenshotted the table here and replicated it so you can see this again. So this is the same one from the previous page. This is still table 22.1. And I've highlighted up the redox systems that are being asked to combine here. Now we can see from my labels just here, the electrons don't immediately cancel. So what I need to do is find a common multiple and effectively scale up the redox systems using that to make sure that the electrons cancel out. So I'm going to multiply redox system 2, everything in redox system 2 by 5, and everything in redox system 4 by 2. You can see that I've done this here, including the electrons, which I have done on the second line because I wanted to get all the chemical formulae in the top line of this. And then what I've done is I've identified that there are H2Os, for example, and hydrogen ions, for instance, as well as the electrons on either side that need cancelling down. So you don't just cancel down the electrons, and remember we have to do that as an absolute minimum, otherwise we don't have a redox reaction because we shouldn't see the electrons in a correct and balanced redox reaction chemical equation. I also need to make sure I cancel down anything else. And this is very clear in lots of mark schemes for OCR-A. So make sure you do cancel down any waters or hydrogen ions or anything else along with the electrons to get this correct answer. That moves us on to question 21 from paper 1, 2018, still on the OCR-A specification. This one starts off with just a little bit of electron configuration work where we start to see a bit of crossover now as we move into the later years of these papers with the transition elements topic. Here we've been asked for the electron configurations of nickel and nickel 2+. Just remember that 4s gets priority all the time over 3D, so it's filled first and it's emptied first. You can write these two at the end here in either order, it really doesn't matter. For the next question, a standard cell is set up in the lab once again, and here is the overall equation. Now, based on this overall equation, I can identify from this electrochemical series, which unfortunately is missing my favorite column, the redox system number column just there, but it doesn't matter. I can see from this overall equation that the two redox systems I'm using are the ones that I've highlighted in this top table for you here. I need to draw a diagram for the apparatus once again. And same as before, I'm going to have my anode, my negative electrode on the left over here, which is going to be demonstrating oxidation. And I'm going to have my cathode, my positive half cell, my positive electrode over here on the right, which is going to be demonstrating reduction. Now, just like last time as well, and it is interesting, these two exam questions were 1 year after another. It is interesting that, again, we've got one of the half cells, because of its redox system information, having the solid nickel metal, and then the nickel 2+ ions is going to have a nickel electrode and then a 1 mole per decimeter cubed solution of the ions just here. And then the other, much like the previous year, doesn't have a solid metal electrode of the components of the solution. Instead, once again, I'm having to use platinum here. You can see I've got separate labels here for 1 mole per decimeter cubed for each of the components of the solution. And I did that for the 2017 exam question as well. Make sure you do this. 100% clarity, please. Let's have as many labels as we can that make sense. Here I've got the standard conditions again, and just like before, because there's nothing gaseous in this apparatus, the pressure was ignored. I just also want to add to this that occasionally they ask about charge carriers. And so what they'll often want you to do is, once you've correctly identified the negative, which is the nickel one here, for example, and the positive, which is the platinum, or you can call it the iodine half cell just here, when you've correctly identified the negative and the positive electrodes, they often ask about showing the direction of flow of charge carriers. The electrons are going to go from the negative electrode, the one that shows oxidation, across to the positive electrode, the one that shows reduction. And the salt bridge here, which must always be labeled, is going to transfer ions in both directions. So make sure you make that extra clear with any additional labels, just in case that comes up in the exam. And it has done before. Moving on to the next question. Same as before, can you notice a pattern? Predict the standard cell potential for this cell. So once again, it is E cell, reduction minus oxidation, with the reduction being the more positive out of the two, and the oxidation being the more negative electrode potential out of the two. Gives me an answer here, which I'm expecting to be positive. And remember, as an extra caution, I am going to start showing these positive signs, even on obviously positive answers of 0.79 volts. Moving on to part C, use the information in table 21.1, which I have given you a little screenshot just here. This isn't in the original exam question, to help you answer both parts of this question. Write the overall equation for the oxidation of iron 2 by acidified hydrogen peroxide. So from the table, I've identified that I need to use iron 2 here, because when it goes to iron 3, that's then undergoing oxidation. So that's the iron 2 getting oxidized. And here I've selected this equation because I've got the hydrogen peroxide in the acidic conditions, because it mentioned that up here. So those are the two I'm combining together, and this is my overall equation. Next one. This is a multi-stage question, and these are becoming more popular. Zinc reacts with acidified dichromate ions to form chromium 2+ ions in 2 stages. Explain why this happens in terms of electrode potentials, that comes up on the old spec papers, and equilibria. Now that's rare on the old spec papers. Include overall equations for the reactions which occur. All right. Now, if we have a look at the bottom down here, this is again a little screenshot of the electrochemical series from the start of the question, and I'm going to use this to describe what's going on. We're being told that zinc is being added to the dichromate just here, and I've identified them in the table. And the goal, as you can see, is to get to this chromium 2+. So how is that happening? Well, in the electrochemical series we've been given, the zinc redox system has got the most negative standard electrode potential, which means it's going to be shifting left when you pair it up with any of the others from this particular example of an electrochemical series. And that's because it's got that greater tendency than all the others to release electrons. So when I pair up the top redox system here, the zinc redox system, with this dichromate redox system, the dichromate redox system is going to shift to the right, and that's going to create chromium 3+ in the solution. Now, chromium 3+ is also in the table up here, in a redox system that is less negative than the zinc redox system still. So as a result, the zinc is also able to reduce this chromium 3+ across to our goal of the chromium 2+. So we go from here to there, which is shown up here, across to there, all because of the zinc having the most negative electrode potential in the electrochemical series snippet we have here. So how do we word that for the exam? We need a framework. We need to compare the electrode potentials We need to talk about shift of equilibrium, and please use the word shift when you're talking about equilibria. We need the overall equations, and we need this consistent pattern then. We need to approach how we predict reactions using the electrochemical series in a way that compares the electrode potentials, talks about shift, and gives the overall equation each time. And we'll see this again with a later question. So here I have the electrode potential of zinc is more negative than the dichromate 6 one, which is what this is just here. I'll often just refer to it as dichromate, but it is dichromate 6. Now, you can have the reverse argument here. So ORA in mark schemes means all reverse argument. So I could have said that the dichromate, the Cr2072-, the dichromate 6 there, its electrode potential is more positive. But I'm going to keep it in the perspective of the zinc. I have a habit of this. The zinc system shifts to the left. So there's that equilibria point. There's the overall equation for what's happening. And like I said, it makes the chromium 3+ that we see in another redox system elsewhere in the table. Now, I don't believe you would ever know this by looking at the question, but the mark scheme actually only required this kind of discussion in the answer once. But I have shown it again here, but I have labelled it as not required, since I don't believe you would actually know not to do that if you were given this question in an exam. So I would give the entire answer here. Don't hold back. Really make sure you've hit all your key vocab. Here we can see that the zinc electrode potential is more negative than the chromium 3. So the zinc system shifts to the left, or the chromium 3 one now shifts to the right. And we see that we have the chromium 3+ being reduced to the chromium 2+. We definitely did need to show this equation to get the final 4th mark. Moving on. The question now becomes very transition elements focused. Initially, I was just going to make this tutorial all about the redox and electrode potential questions, but there's such a massive crossover, particularly with the end of this 2018 one, and also looking at the 2019, loads of crossover. So let's have a look at this one as well. 3 different reactions of copper compounds are described below. We've got aqueous copper 2 sulfate. Now, in aqueous copper 2 sulfate, this bit is really important. We have this complex ion. That's something you are expected to know. And with excess aqueous ammonia, in a ligand substitution reaction, a deep blue solution is formed containing an octahedral complex ion C with a trans isomer. That's a lot of vocab, and it's also a lot of reliance on making sure you know the colours of inorganic ions and complexes, which I will say OCR has put in a table for you to use, and I'll put a link to that at the bottom of the video description. Then in reaction 2, copper 1 oxide reacts with hot dilute sulfuric acid in a disproportionation reaction, and a blue solution, D, which is going to be copper sulfate, sulfuric acid and copper, come on, we know it's going to be copper sulfate, and a brown solid. This is really unfortunate. I would actually describe it as maybe a copper-coloured solid, but you can't for the exams. You've got to say it's a brown solid for this, because you can't say it's copper-coloured copper. So it's a brown solid for this, and it's E are formed. I'm already annotating here because I know the reaction of this. I know it's a disproportionation. It's in the interconversion section of the transition elements section of Module 5. So these are known reactions. These are not processes they're bringing up purely for the context of the exam. These are reactions that are mentioned in the colours of inorganic ions and complexes summary sheet, and they're clearly outlined in the spec as things you need to be aware of. Then reaction 3, again, a bit more complicated, massive link here to module 2. Copper 2 oxide reacts with warm dilute nitric acid. So I'm going to assume here that I'm making some sort of copper nitrate, copper 2 nitrate, for example. Unreacted copper 2 oxide is filtered off and the solution is left overnight in an evaporating basin. Quite rare to discuss that in chemistry. A hydrated salt, here's your module 2 link, XH2O there, so we know we're going to have waters of crystallization. F crystallizes with the percentage composition by mass, so this is going to include these. So you need to see how many you can make from the formula. Identify C to F. So all the way through here we've got these letters, and we've got to give identities for all of them and include any equations, any changes in oxidation number, and working all the way through. And notice up here, please, it is level of response. So you really need to think about a clear and logical layout. So I would split it up by reaction, which is exactly what I've done. I would make it bullet pointed and clear. Just don't put any bullet points next to chemical formula because it could make them look like a free radical. All the way through here, I'm going to go nice and stepwise. So for reaction 1, I know that I had the hexa-aqua copper 2 complex ion just here. With excess ammonia, I'm going to form this deep blue solution, which does have a 2:4 ratio between its monodentate ligands. So it is going to have cis and trans stereoisomers. And don't forget the 4 H2Os. I find people forget the 4 H2Os. When I'm drawing out the structure down here, I've got the trans stereoisomer. Now, you might be looking at this and thinking, you've drawn them in the wrong places because you're meant to show them at the top and the bottom. No, I'm not. I'm meant to show the H2Os 180 degrees apart. So I'm meant to show the 2 in the 2:4 ratio 180 degrees apart to get the trans stereoisomer, which is exactly what I've got here. For another video about cis-trans stereoisomerism, you can click the little link at the top of the screen now. For reaction 2, I've got the copper 1 oxide with the sulfuric acid to make the blue solution here, compound D, which is copper 2 sulfate, and the brown solid there, which is the copper compound E. This one's really over before it started. I've got the copper 1 just here. I've got copper 2 plus here, so that's going to have an oxidation state of +2, which perhaps I should mention in my answer here, so you can add that in. And the copper here is going to have an oxidation state of 0. So perhaps I should include them in my answer as well. So feel free to annotate and add that in here. I suppose there's space here to do it, so you could always do that there. For reaction 3, I'm going to assume here I'm making the copper 2 nitrate for this because I've got an oxide and a metal reacting together, which makes me think of the module 3 topic of the group 2 metals and how their oxides react with acids perhaps. I've also got the percentage composition by mass, which I've got these ratios from. So I've not shown all my working out here because it's quite straightforward working, and I'm sure you can work through this yourself to get to the ratios here between these. Now, remember what I said before, this is going to be the product, but we're told that it's a hydrated salt. So this ratio of the elements includes some H2Os, some waters of crystallization, which you can see I'm representing here in this right-hand part of the structure with my 3 H2Os there. You have a lot of oxygens here, so you wouldn't just write out the molecular formula of CuH6N2O9 and leave it at that. You've been given a lot of information here in the question, particularly this hydrated salt aspect, so I'm definitely going to include this .H2O to represent the waters of crystallization. That takes me on to question 18 from the 2019 paper 1, again still on the OCR specification. And like I said before, this question starts off very transition elements based. But once again, all the answers in this really are on the colours of inorganic ions and complexes sheet that OCR have. You are expected to know all of these for chromium, and they're all on that list. So you must make sure you know your aqueous ion formula, which I can't reinforce enough. Look how weighted the exam questions from 2018 and 19 are here based on knowing these complex ions and colours and formula. You've got to make sure you get to grips with this. And I always say this to my students, and I'll say this to you as well. Please don't underestimate transition elements. It's a major part of the exams. It's a very good way for them to get quite wordy content into paper 1, which we know is very maths focused. So, in experiment 1, student adds an excess of aqueous ammonia to a solution containing the hexaquachromium 3 until a purple solution is formed, which I know is this because I know my complex ion. So that's just a matter of fact. I would class that as recall. Then in experiment 2, the student carries out the following reaction sequence. So in step 1, they add sodium hydroxide slowly to a solution containing the same complexes up here. A grey-green precipitate forms. Again, from knowing my formula, I know that it's this, the chromium 3 hydroxide precipitate. An excess of the sodium hydroxide is then added to the boiling tube. I know that the precipitate is going to dissolve to create this complex ion. Careful with the charge. H2O2 is added to the mixture and the boiling tube is heated. A yellow solution forms. I know that that's the CrO42- again from the sheet. It is there. It's mentioned on it. In fact, I can tell you that this is towards the left-hand side, in the bottom left-hand corner of the sheet, because I know it that well. The step 4, once again, the solution in the boiling tube is acidified. The solution now contains dichromate 6. Now, if you know your organic chemistry, you'll know that this is orange, but again, it's mentioned on this big OCR sheet. The answers to the questions then effectively take me through all of the descriptions that I've just provided, knowing that the formula of the purple solution in experiment 1 has got these 6 ammonia ligands around the chromium 3+. Knowing the equation, the ionic one is fine. To form the precipitate here, the chromium 3 hydroxide precipitate is crucial for part 2. Drawing the 3-dimensional diagram with those 6 OH- ligands all the way around the chromium 3, giving me that 3- charge on the outside just here. Knowing the formula of the yellow-colored ions in experiment 2, step 3, and knowing the color of the Cr2O7 just here being formed in step 4. It's all stuff that I can learn from that sheet. So we've got 1, 2, 3, 4, 5, 6 marks here. Just as many marks from an NMR, infrared, mass spec, molecule analysis question in organic chemistry. So we must make sure we know all these colors of ions and formulae. Please refer to the sheet, which I will put a link to in the video description. Moving on to part B for this question, vanadium ions have got 4 common oxidation states. So here they are, and these are the ions that contain the vanadium in these oxidation states, and those are the colors. These are not ones you're expected to memorize for your specification, so don't worry. Electron configuration question to get started with. This shouldn't be too much of a problem as long as you remember that 4s is emptied and filled before 3D, so make sure it ends in 3D2 for the vanadium 3+ ion. Then we've got this electrochemical series, which has got the amazing column here, the redox system number column, best column ever. And we're told that the student adds excess iron, there's the excess iron, to a solution containing VO2+, there's that, and observes that the color of the solution changes from blue to green to violet. Now, the green here is present on both sides in the table. So what I'm suggesting is the iron, because it's got the more negative electrode potential than redox system 4 here, the iron is going to reduce the vanadium over to the vanadium 3. The vanadium 3 is in the table elsewhere, so now it becomes eligible to also be reduced by the same iron because we're told it's in excess. And the vanadium 3 gets reduced to the vanadium 2, and that accounts for all the color changes here. What I would do is consider writing the colors just underneath the formula here using the table from the top, because that might help you track. Similar to the chromium question, though, that was shown before, can you see how in this equation we make something that's also present elsewhere in the table? So we did it in the chromium question in the 2018 paper, which made chromium 3+, which was shown elsewhere in the table in a different redox system. That seems to be a trend that they're following with this. So what we want to make sure when it comes to the exams that we're preparing with is, can we draw an apparatus? Can we use the electrochemical series in this way? Are we vigilant to see if an ion that we're producing is then shown elsewhere in the table? That's our kind of skill set. For the question, we need to now explain the observations. So I'm going to follow a very similar setup that I did before in terms of how I describe the electrode potentials to explain the shifting equilibrium here and to describe how I'm actually achieving these changes in oxidation state. I've also given you a little tiny summary just here of what's going on linked to my labels on the table. I'm going to keep the question focused on the vanadium though, because even though the iron is in excess and it is present in the description of the question, the vanadium is the main focus. So the vanadium oxide just here, so the VO2+, so that would be classified as the vanadium 4 oxide, just there it is. Goes to vanadium 3+, and then to vanadium 2+. Why does this happen? Because redox system 4 is more positive than redox system 2, the iron one. System 4 equilibrium shifts to the right. That creates the vanadium 3+, we know that. Redox system 3 then, the one with the vanadium 3+ in, is less negative. Now, I've said less negative here, and I said more positive for the other. You can have the reverse argument for this as well. So you can also actually say, which isn't necessarily the reverse argument, it's just a different descriptor, you could also still say that this one is more positive. I know that it's a negative number, but you actually can still describe it as more positive. I just don't like doing it. So redox system 3 is less negative than redox system 2, and system 3 equilibrium shifts right, which gets me to that purple solution. Construct an equation for the first color change from blue to green. I'm just combining redox systems 2 and 4. Not too complicated, just make sure the electrons cancel. So for 2 and 4, we can see that we're going to need to do a multiple of redox system 4 to make sure that the electrons cancel out. And that's exactly what I've done here. Moving on, and we head towards a redox titration style question here. We've got iron 2 gluconate is the active ingredient in some brands of iron supplements. Now, this has only got one iron in, and one ion in, and a load of other stuff here. A lot of carbons, hydrogens, and oxygens in this formula. And the student carries out an experiment to determine the mass of iron 2 gluconate in one tablet of an iron supplement using the method below. Stage 1, the student crushes, I noticed this, I thought this was quite sneaky. The student crushes 2 tablets, even though they only want to study 1 tablet, so we're going to need to divide by 2 at the end, and dissolves the powdered tablets in dilute sulfuric acid. The student makes up the solution from stage 1 to a 250 volumetric flask. That's a little bit like preparing a standard solution, it's just we don't know the concentration of this, so I'm not going to say that it's a standard solution, but if you're trying to link it to a previous practical, it is a similar technique. You're still using a 250 centimeter cubed volumetric flask to prepare a solution. It's just not a standard solution. The student then titrates 25 centimeter cube portions of the solution obtained. So there's a ratio here of 1 to 10. Obtained in stage 2 with 0.002, quite low, mole per decimeter cube potassium manganate 7 solution, which is going to be the KMnO4. Which is often represented in questions just by using the ion of MnO4-, because the group 1 metals here are quite disposable. We're not really particularly bothered about them. The student obtains a mean titer, an average titer here, of 13.50 centimeters cubed. In this titration, there is a ratio of 1 to 5 between the manganate 7 and the iron 2 ions. First one, explain why the student uses such a low concentration rather than the usual one, which would be the 0.02 mole per decimeter cube. This is quite a lot lower. You've got to then think, like I said up here, what does this cause for? If you think about the setup in a lab, if your solution in the burette is significantly more diluted than you would normally have it, then you're going to need more of it from the burette in order to neutralize in a regular titration, but here just react with the components in the conical flask. Try not to use neutralize here because this isn't a neutralization reaction, this is a redox titration, but it's hard not to picture a titration in that neutralization context, isn't it? So if I have the solution in the burette significantly more diluted, I'm going to need more of it to complete the reaction, let's say. What's that going to change? Well, when we think about percentage uncertainty, the bigger the reading that we're going to need from the piece of kit, the lower the percentage uncertainty, because the percentage uncertainty calculation is going to take the error margin of the apparatus and divide it by the reading we took. So the bigger the reading, which is the denominator, then the smaller the percentage uncertainty. And so you could consider that to be a stock descriptor here for when we use either an increased mass of something using a balance, or if we use a larger volume of something in a different piece of kit like in a burette. Now for the next bit here, you've got the big calculation. You can see here I've done all my working out line by line, and that's not just because I'm a teacher, it's because I am aware that this is going through a series of stages that I'm going to need to show little by little all the way through to make it clear to the examiner. In case I mess up and write the wrong number up here, I want error carried forward, which is always allocated for these if you have clear working out. We're going to use the student's results to determine the mass in milligrams of the iron 2 gluconate in 1 tablet. Remember what I said before, give your answer to 3 significant figures. What I'm effectively doing is I'm going from this titer value here for the manganate, and I'm working my way back up all the way up to the top. So I'm going to get the moles of the manganate. I'm going to use this ratio to find the moles of the iron 2 in 25 centimeters cubed. I'm then going to scale up to the 250, and then I'm going to relate that to the formula up here. I'm literally walking in reverse through the stages in an unstructured calculation. The fact it's a redox reaction means nothing here, really, because it's all about just working through the stages in the reverse order. So take your time. Here, using the average titer and the concentration, quite low, remember, I've got my moles of the manganate. The ratio is 1 to 5, so I times by 5, and that's the moles of the iron 2 in the 25 centimeters cubed. I scale up to the big solution by timesing by 10, and that gives me a value of 1.35 times 10 to the power of minus 3 mole of the iron 2 in the big 250 solution, which is from the 2 tablets. Do watch out, because I did notice in another question recently they had a 1 decimeter cubed volumetric flask instead, and so that wouldn't be a times 10 conversion, that would be different. I believe that would be a times 40. Then, this bit is the head scratcher sometimes. Can you see there's only one iron in here that I mentioned before? That iron is iron 2 in here. And so the number of moles of iron 2 in the 250 solution, because that comes from this formula, it's equal to the number of moles of that entire formula. So here, if I want to know the mass of that formula in the tablet, or 2 tablets it should be at this point, I'm going to do the moles I have for the 250 solution multiplied by the molar mass, quite a big value, for this whole structure. So the moles of the iron 2 in the 250 solution have led me to understand that that's how many moles of the iron gluconate, is it called? Not something you normally study. Yeah, iron 2 gluconate. And that allows me to get a mass of the iron 2 gluconate here by multiplying by the full molar mass. I'm then going to divide this by 2 to get the mass in grams for 1 tablet, and then times that by 1,000 to get it into milligrams, so my answer is 301. Don't round up until you're right at the end here. The question here finishes up a little weirdly, where we're asked to choose which iron supplement, A or B, from the table would provide the greater mass of iron per tablet. It's really unusual, and I do apologise. I'm leaving the mass values here in milligrams because I'm going to quote my answer in milligrams at the end. And I know strictly for these calculations I should use grams, so I am kind of fudging this a little bit. But the main reason is it's only 1 mark, so I don't want to dwell on this for too long. This is a really strange question in my opinion. The way I've answered it is, this is the mass value for the entire iron compound each time. So what I do first for both of them is I work out the number of moles that I have of these structures in these masses. So here I've got my mass here, and I've got the molar mass there for the iron sulfate, and I'm classing this as my number of moles, even though I'm not strictly using grams here, I'm using milligrams for the masses. Then what I've done is I've taken this mole value, this pseudo-mole value, and I'm going to multiply it by the molar mass this time, not of the entire structure that I used here, otherwise I just go back to the start, but this time just of the iron, so the 55.8. And what that's going to do is give me a mass, which is going to be a proportion of the other mass, that's now just iron. And I do that for both of them, and you can see here that I end up with a greater milligram iron value for supplement B. So for each of them, I find the moles using their formulae and the mass values from up here. And then for both of them, I take that pseudo-mole value and I multiply by 55.8. Now, really, I didn't need to do this final stage. I could have just used these mole values, but I wanted a little bit more clarity on the page for this. And so by seeing this number was greater than this number, I could have stopped there and just said it's supplement B. There was no marks here, of course, for my working out because it was only 1 mark. That's the end of these 2017, 18, and 19 exam questions on redox and electrode potentials and on transition elements. If you found the video helpful, I would really appreciate it if you could leave a like before you go and consider subscribing to stay updated. Don't forget to check the video description for links and extra information. And until next time, happy revising.